All right, fantastic. Welcome back. Hope you had a lovely lunch in the sunshine. We have our next sessions about to start now, more masterclass this time, so you'll really get to be able to dive deeper into some of these subjects. And to kick us off, we have Dieter here, representative of the DFINITY Foundation, going to speak to you about some more innovation and different things that have been happening. So I'll let you take it away.
Thank you for the introduction. Good afternoon, ladies. Good afternoon, gentlemen. It's very much a pleasure for me to be here today and to talk to you about how to bring the networks ICP, BTC ETH, and others in the future closer together, thanks to what we call chain fusion technology. So in this talk, I would like to first give you a quick crash course introduction to the Internet Computer Protocol. That's what the DFINITY Foundation that I'm working for is building or is contributing to a large degree. Then I'll talk about what is chain fusion technology, give you a brief motivation of it, then give you two building blocks we use for this, so for integrating chains, namely chain key ECDSA signing. That's an advanced form of threshold signing protocols for ECDSA and also other protocols coming shortly. Then talking about HTTP outcall, that's a mechanism for smart contracts on the internet computer to connect to Web 2 services securely and communicate with those. And after those two building blocks, I'll talk about two blockchain integrations, the one with the Bitcoin network and the one with the Ethereum network and EVM chains in general. And I'll conclude with going through some D-apps that use chain fusion in the ICP ecosystem. So let's get started with the crash course on the Internet Computer Protocol. Really very high level. The whole talk is very high level and non-technical because it's more a generic audience here. So let's get started. So the Internet Computer Protocol is powered by nodes. So that's the hardware that powers the protocol, and those are located all around the globe. So there's, first of all, it's servers, bare metal servers, no VMs, virtual machines are allowed, and also no public cloud placement is allowed, because this would lead to a less decentralized network because of few public cloud providers that would host most of the nodes. So the idea is really to have this node pool very decentralized, and those nodes are operated by independent parties in independent data centers. The data centers are distributed in different countries or geographies, and those are in different jurisdictions. And with those four dimensions of decentralizations, we get a very, very decentralized node pool, currently around 1,000 nodes. And now those nodes are used by the protocol to form so-called subnets or subnet blockchains. Each subnet, so the subnet is the basic building block of the IC, and each subnet is its own blockchain and running its own instance of the ICP consensus protocol. And the subnet is the place that replicates computation and storage on the nodes that form the subnets. And every subnet runs concurrently with the other subnets, giving the whole internet computer a lot of throughput and storage capacity. And one important part is that the four dimensions of decentralization that the node pool is comprised of are carried over to each subnet by choosing the nodes appropriately through the protocol. This process is called deterministic decentralization. And again, so it means that the nodes of each subnet are formed from nodes from independent node providers that sit in independent data centers, which are in different countries and geographies and different jurisdictions. So carrying over the decentralization of the node pool to each subnet, that's an important thing. And now we have many of those subnets. Currently it's around 35 to 40, I don't know the exact number. And what we get is a scale-out architecture like public cloud. In a public cloud, you can add more machines to get more capacity. On the internet computer, you can add more machines and then form subnets to increase the capacity. It scales more or less linearly, so very much like public cloud, but it's a blockchain. So what you get is really a platform to run so-called canister smart contracts. We chose those names because the canister is a container for code and data of the smart contract. And each canister runs on one subnet and is replicated on the nodes of this subnet. And now all the subnets execute concurrently, so we get a very, very high throughput of transactions on the whole internet computer, because we have 35 concurrently operating subnets, or shards if you will, but it's a more generic architecture than shards. And now, in a very high level, what we have is, with this architecture, a crypto cloud. So you get blockchain-like security because every subnet is its own blockchain, and cloud-like scalability. Now, so much to the introduction to the Internet Computer Protocol, which is a very scalable layer 1. Next, let me introduce chain fusion technology. So the basic idea behind chain fusion is the following. Chain fusion is integrating or fusing, hence the name, the ICP, the Internet Computer Protocol, with other chains like Bitcoin, Ethereum, and so on. And why do you want to do this? So this gives you, so you can build cross-chain DApps, essentially DApps that span multiple blockchains, but the user experience is just as simple as it would be implemented on a single chain. So great user experience, but still leveraging good properties of every chain. And that's the basic idea behind it, because different chains have different strengths. For example, the Bitcoin and Ethereum networks, they have very high liquidity in their core tokens. Also, they have a very, very high replication factor, which is good for certain use cases, but also transactions are very expensive and you can't do much computation on them because it's too expensive and limited. That's why you can, for example, do heavy computation on the Internet Computer Protocol and use Bitcoin and Ethereum and also other networks for other purposes in which they are strong. And that way you build DApps out that span multiple blockchains, and you get the best of each chain for your DApp. And so far, what we have covered in terms of networks is the Bitcoin network, the Ethereum network, multiple EVM chains. So essentially, you can have any EVM chain that has a public RPC node. Solana is coming up shortly, and then additionally, there will be other networks integrated either by the DFINITY Foundation ourselves or by the community. There are two core building blocks for chain fusion that we use. So the one is signing transaction for other chains on-chain, meaning that you can sign a transaction for the Bitcoin or Ethereum network on the ICP blockchain without the private key being anywhere. This is called chain key cryptography, chain key signing. It's based on threshold cryptography. The Internet Computer so far has implemented threshold ECDSA that has been deployed some time back and is used for Ethereum and Bitcoin. And soon there will also be Schnorr and EDDSA coming up to support a larger variety of blockchains. So practically all relevant blockchains are supported with those three schemes. And the other basic building block is securely reading from and writing to other blockchains. So meaning reading state from other blockchain, for example, from the Bitcoin network, reading blocks or specific parts of the state, and then writing back transactions that are signed with the first building block to the other blockchain. And this way you can interact from a smart contract with other chains as if the smart contract were a normal use on this chain, which is very powerful. We have three different approaches used so far for this integration on the second building block. One is verifying the consensus of the other chain fully on ICP, which is done for the Bitcoin network. I'll talk about this shortly. The other one is using a light client to verify consensus of the other chain, which we have experimentally up and running for the Ethereum network. And then the third one is to read from multiple RPC providers, so Ethereum RPC providers, and do an in-smart contract consensus over the responses and use this value for reading state and writing back via those as well. And this is done for the Ethereum network and other EVM chains and will be done likewise for the Solana network and potentially others that are coming up. So those two building blocks, I will now talk a bit more in detail. So let's start with chain key ECDSA signing or threshold ECDSA. So the basic idea is, on the right side here, you see a canister smart contract holding this green ECDSA key, and this ECDSA key allows the smart contract now to derive addresses for other networks, like for the Bitcoin network, for the Ethereum network, and then receive funds on those addresses on the native network, and then use essentially threshold signing to create the signature on transactions and send this transaction out using some building blocks to the respective network. So this allows you to have a smart contract that interacts like a user with other networks. Now, how does it work under the hood? So threshold cryptography is the keyword here, meaning that we have so technically one specific subnet, which is a high replication subnet with around 30 nodes, and each of those nodes holds a share of an ECDSA private key. The actual private key has never been known by anybody and is never known by anybody, and whenever a signature is required to be computed, the subnet performs a multi-party computation or MPC protocol in order to compute the signature, of course, without reconstructing the key. So multi-party computation is also a mechanism that leading-edge commercial custody solutions use those days, because it's a very secure way, thanks to cryptography, to secret share a key to multiple instances and then perform operations collaboratively. But only one or a few entities can do nothing with their key shares. That's the main idea here. So essentially what you have is a completely decentralized signing protocol implemented on the blockchain, so the next generation of hardware security modules, if you will. And now any canister, like here on the left side, on the Internet Computer, on different subnet or in the same subnet, can now use a very simple API to interact with this threshold signing protocol. So first of all, the canister can get its own public key and then do stuff with it with other networks, like derive a Bitcoin address or an Ethereum address. And it can request a signature. And as I said, this is then computed via multi-party computation by this threshold ECDSA subnet. And the signature then can be used, can be done, for example, on a transaction to the Ethereum network and then can be sent out to the Ethereum network. So that's roughly how it works. Very easy API and a very, very secure and decentralized way of signing messages, because the key is decentralized throughout the globe and no one has ever seen it, no one will ever see it. And threshold ECDSA, as I said, is already live on the Internet Computer, has been for almost 2 years, I think. And what's upcoming this summer, I think late July or August, will be threshold Schnorr and EDDSA, and those will allow further integrations. For example, Bitcoin ordinals and like runes, for example, also, they can be handled with Schnorr only, not with ECDSA. So this will be enabled fully on-chain. Also an integration with Solana, as I mentioned already. Then Cardano, Algorand, and many other blockchains that use EDDSA will also be integratable with the Internet Computer. And then you can build dApps that use the goodies of any selection of those chains that you want, and that will be integrated. So this is just a list of potential candidates, and the community of the Internet Computer will see which ones they want to integrate next and work on next. So, and what this gives us is a very, very nice ecosystem where smart contracts on the Internet Computer, here shown on the right, can transact any kind of crypto on any kind of blockchain network, like Bitcoin, Ether, USDC on Ethereum, any kind of meme coins, Solana tokens, so on. So this is really cool, and you don't have any limits here on what kind of tokens you can do. So you can use ICP as a token hub, so to say, and can have a very, very wide variety of use cases. So this was the first building block, threshold cryptography. The next one is HTTPS outcalls. HTTPS outcalls, very simple at the high level. So a canister smart contract is able to make a call to a Web2 service and get back a response. Of course, it's not so easy because the canister smart contract is replicated on many machines. So what happens in the background is, I show you 4 machines. Every machine that hosts this subnet where the canister is running makes the same call to the Web2 server, and then the Web2 server provides back a response to each of the calls. And then these responses are subjected to a transformation function that removes things like timestamps or session identifiers, and then the output of the transformation function on each node is run through consensus, and if there is consensus found, which means at least 2/3 of the nodes agree on the result, then the canister receives a single response back. So from the canister perspective, it is really like sending a request to Web2 server and getting a response back if everything works out. So very powerful way to integrate with Web2, and you will soon see why we need this. But before that, let's talk about the Bitcoin integration. So the Bitcoin integration uses only the first building block I've discussed, and instead of the second one, it uses a native integration, which is even stronger. Let me talk about it now. So the Bitcoin integration, here you see on the left side the Bitcoin network, on the right side you see one subnetwork of the Internet Computer Protocol. So it works as follows, that one subnet has been enabled to run so-called Bitcoin adapters here on the bottom, these orange components, and then also one Bitcoin canister smart contract here on the top that runs most of the logic. And what happens is that those adapters here, they connect to the Bitcoin network, act like a regular Bitcoin node towards the Bitcoin network, and whenever a new block is mined in the Bitcoin network, the block is ingested into the Internet Computer, sent up the protocol stack to the smart contract, and then the smart contract validates the proof of work consensus fully on-chain in a smart contract. If it's valid, so if the block is valid, the smart contract extracts all the transactions and the transactions inputs and outputs with the goal of essentially keeping track of all the UTXOs of the Bitcoin network. So essentially all the unspent coins of the Bitcoin network. And this allows now any canister on the Internet Computer to query this Bitcoin canister for the UTXOs of a given Bitcoin address. And this allows you to determine the balance of any Bitcoin address on the Bitcoin network. And it also allows you to get your own UTXOs as a canister for the keys that you control with threshold cryptography, and then you can make transactions by doing a threshold signature using this first building block, threshold signing, on the transaction comprising some UTXOs that you own, and then you can send this transaction out through the Bitcoin adapters, and they go to the Bitcoin network. So that's roughly how it works. The nice thing about it is that it's essentially a Bitcoin node that's fully on-chain, which is very nice. And it's a completely trustless integration with the Bitcoin network, which means there are no intermediaries like bridges required. It's completely trustless. Therefore, we have only the trust assumptions of the Bitcoin network and of the internet computer, and no additional trust assumptions or parties being required. This is the strongest way you can integrate with the Bitcoin network. No additional assumptions to be made. So that's a very, very nice showcase on how we can do integrations with other protocols. And now let's jump over to Ethereum and EVM chains next. So Ethereum and EVM chains use both building blocks that I mentioned. So threshold signing is clearly used again for signing transactions. Nothing new about this. I explained it already. And now for the communication level integration with the Ethereum network, I need to take a step back and explain, for those who don't know, how Ethereum is usually accessed. So if you write an Ethereum DApp, you have two options. You can run your own Ethereum node, or you can rent capacity or API calls at one of those Ethereum RPC providers like Infura, Cloudflare, Public Node, and so on. That's what most people do. And we chose also for this integration to leverage those RPC providers in a way that we implemented from the DFINITY Foundation side an EVM RPC canister here in the middle, which is more or less an on-chain EVM RPC API. So it exposes the API of those RPC providers that are Web2 services on-chain on the internet computer. And now if a client canister makes a request to the EVM RPC canister, to this on-chain EVM RPC API, the canister makes requests, the same request to multiple of those RPC providers, and if they all respond with a consistent response, the consolidated response is sent back to the client canister. Otherwise, an error is sent back, or respectively, the fact that it's not consistent. And this allows you to get a decentralized way of querying state from the Ethereum network. And of course, you all can also submit back transactions to the Ethereum network that are being signed with threshold cryptography, as in the Bitcoin case. Now that's the way we can get access to Ethereum mainnet and of course testnet and other blockchains, like we have a couple of layer 2s already, like the Arbitrum 1, Base, and Optimism protocols. And those are reachable through a handful of RPC providers that are hard-coded or installed as defaults in this RPC canister. And users can also bring their own RPC provider, so to say, provide an URL for their favorite RPC provider or providers and an API key, and then further RPC providers can be used to even reach out to more diverse sets of EVM chains or use different providers for other reasons. So that's roughly how the EVM integration from a communications perspective works, and then of course the threshold signing is used for signing transactions, and this way we have a bi-directional communication between the networks without involving any third parties besides those RPC providers, which are typically well-reputed business entities. So this was a very high-level overview of how the Ethereum integration works, and next I would like to give you a rundown on a couple of interesting DApps on the internet computer that are using this chain fusion technology in one way or the other. So one very interesting, because very early one, is CK-BTC, stands for Chain Key Bitcoin, alluding to the use of chain key cryptography, like threshold cryptography. So this token works in a way that if somebody owns Bitcoin on the Bitcoin network, they can transfer some Bitcoin to the CK-BTC minter. This is a smart contract on the internet computer that locks up the received tokens. And once it has enough confirmations on the Bitcoin network, like 6 confirmations, 1 hour, it mints a corresponding amount of this twin token, the CK-BTC, in the CK-BTC ledger. And this twin token is now a token that's available on the internet computer, and it's backed 100%. So every CK-BTC is backed by one real BTC locked up in the CK-BTC minter. And now the user who owns the CK-BTC can transfer it to other users or to smart contracts. And what we have with this is a very low fee, high throughput, and low latency way of transacting this twin token to the Bitcoin token. And applications obviously are DeFi, like taxes, social fi, like sending, making peer-to-peer payments with people, and any form of payments. So this is very interesting because this CK-BTC is also built on the Bitcoin integration I explained earlier, is completely trustless, does not involve any intermediary party. Something analogous was done for for Ethereum, for the Ether token and for the ERC20 tokens. So far we have CK ETH available on the internet computer, a twin token to the Ether token, and then CK USDC is the first ERC20 token available on the internet computer. And more will come, and this will be done based on a vote of the DAO that governs the Internet Computer Protocol. So the DAO will vote which tokens they want to have next. This might be other stable coins, this might be meme coins. Yeah, we will see what's coming up. And all those CK ERC20 tokens are handled with the same minter, and every new token gets a different ledger smart contract. That's the equivalent of an ERC20 smart contract on Ethereum. We have the ICRC1, ICRC2 token standard on the internet computer. And those twin tokens, again, can be transferred very cheaply with low latency and high throughput on the internet computer, and yeah, similar use cases as for BTC. So another interesting application is the OIC wallet, stands for so the OIC wallet, it's a network custodial wallet that's multi-chain. So currently it supports the Ethereum chain using threshold cryptography. And what it can do is it can hold Ethereum assets like ETH itself and any kind of other ERC20 token, can hold this token for you in the internet computer using threshold cryptography. So you don't have to take care of the private key, but it's taken care of by the network using the secret shared key and multi-party computation for making transactions. So you only need your secure login to the internet computer, and then the internet computer manages all the keys for token custody for you. And yeah, it's an easy system that integrates multiple networks, and you have a very, very powerful wallet at your hands. So that's still an experimental state and will be improved in the future by the foundation, hopefully also by the community. Another interesting application, ICDEX, so the IC Decentralized Exchange. This is a project that's a fully on-chain order book exchange. So fully on-chain means that the order book itself is completely on-chain. It's not an AMM, but it's a real order book like Binance or Coinbase. Fully on-chain means it's hack-proof, unlike Web2 services, and it uses chain fusion technology, mainly threshold ECDSA, for the BTC and ETH integration. Another interesting product is Helix Markets, built by a Zurich-based team. This is a hybrid order book exchange, meaning it's not fully on-chain, but the network-based custody is on-chain, so token custody is again being done using threshold ECDSA, like in the OIC wallet, fully on-chain. And the order book and the order matcher are off-chain components for the reason of higher performance. So essentially it feels like any Web2 exchange, but the token custody is done on the blockchain, so the thing that happened with FTX, for example, cannot happen here that easily, which is very good for security and trust towards the customer base. Yeah, and what they offer also is native cross-chain swaps of tokens. So you can swap native assets of other blockchain networks using this exchange on ICP. This is a pretty cool project. Have a look at it. Another interesting project, ChainKeyX. ChainKeyX is a decentralized crypto neobank. So what it means, it has some of the core features of a bank, of a traditional bank, but implemented fully on-chain without any off-chain components, and for crypto assets. And currently supported assets are BTC and ETH, and you can swap, borrow, and earn interest on them. And yeah, the adage they use is not your keys, not your coins, and it's nice to see this slogan from a bank. Next, the Omnity network. The Omnity network is an omni-chain interoperability protocol that integrates quite a bunch of other chains with the internet computer protocol, and then it allows you to send messages between those chains and then transfer assets and all those things. And they use different approaches also for different chains. For example, they have light clients for the near and Tendermint protocols and use other technologies for other protocols. And one thing they're also very early in is this Bitcoin rune. So this is this new kind of Bitcoin inscriptions that realize fungible tokens on Bitcoin, and they were the first ones to have wrapped runes using chain key technology that are available now on the Internet Computer Protocol. And you can trade them here with lower fees than Bitcoin fees would be, which is very nice. Next, Orally. Orally is a decentralized Oracle network, so meaning an Oracle network that's implemented in a completely decentralized way by implementing it on the ICP platform, not requiring any extra entities like their own consensus network, for example. This means they don't make any additional trust assumptions, they just use an available protocol and then integrate with lots of other blockchains and provide Oracle services. So fully decentralized, trustless, and also very low fee compared to other Oracle networks. Also a very interesting project thanks to the breadth of other networks they have been integrating. Another interesting project, Bionic.io, that's an ordinals marketplace. So it's the world's fastest Bitcoin ordinal marketplace, and you can do all kinds of stuff with ordinals, like sending, receiving, inscribing, buying, selling, swapping, and so on. And soon, with the upcoming Schnorr signature scheme, they will also be capable of doing the issuing of inscriptions on the Bitcoin network fully on-chain using the Schnorr threshold protocols. This will be very nice because it will be the only and the first protocol worldwide, or the first ordinals marketplace doing that fully on-chain. And of course, it's all non-custodial, powered by ChainKey Crypto. Another interesting project is Loca Mining. It's a decentralized mining pool where all the mining pool logic, like rewards distribution, is implemented completely on-chain. Of course, the mining is done off-chain in ASICs, clearly. And they also offer things like a marketplace for forward hash rate contracts, and you can earn native yields for Bitcoins. Also an interesting project, still rather early. And now the last project I want to mention is the OpenChat, oc.app. It's a messaging service that's 100% on-chain, running on ICP. And the interesting part of it is the chat accounts are also wallets, which means you can send and receive tokens, like for example ICP, or the Bitcoin Twin token on ICP, or the Bitcoin or the Ethereum Twin token. So it's a full SocialFi D-app. It's interesting also, you can try it out for free. And yeah, you can send Bitcoin, for example, peer-to-peer to your friends with low fees because it's the on-chain Bitcoin on the internet computer. That's the final one I want to talk about. And yeah, I hope I could now give you a rough overview of what the internet computer protocol is doing in the scope of integrating with other blockchains using the chain fusion technology. And I'm sure there will be many more cool things to talk about in the future in terms of other chains being integrated and other technologies coming up. And this is it from my side, and we have a couple of minutes for questions, I think. Yes, of course.
How many percent, I mean, how much, as far as I heard, is like layer 2 for BTC?
Yes, you can see it is a layer 2, yeah.
Yeah, how much Bitcoin for now?
How much?
How much, I mean, how many Bitcoins on the layer 2 on ICP right now?
100 or 200, it's, yeah, something like this. So it's growing steadily. Yeah.
And what is the dynamic?
So it has been growing steadily since the beginning. There have been ups and downs, of course, of people trying it out, moving out again. But overall, it's an upward curve. I can't give you the exact figures, but it's reasonable. Yeah, it's growing upwards.
Is there like vector for institutionals or just for private physical persons?
So for institutionals, the Internet Computer Protocol has some integrations with custody providers. If you want to go in this direction, so those are coming up. There's, I think, a COPPA integration is either done or close to be done. There might be Fireblocks integration at some point coming up, so that you can do then ICP custody, and ICRC will be the next step here. This is also in the pipeline.
I mean, your position to make it more for physical persons, for hamsters like me, or mostly for e-money?
So it depends. I mean. So definitely many of the applications that are being built are for normal people to do, for example, to use the things for D-apps, like for example, trading. This is for regular users, but also we are working on getting institutionals in, as I said, by having custody solutions. And because the solution we use for the chain key cryptography, so the threshold signing, this is a very secure solution to store assets on chain in a custodial way. It uses similar technologies than the big custody providers, just with many more nodes, like 30 nodes for MPC protocol that runs threshold signatures. And this gives you a very secure way of doing custody. And there are attempts now to also approach institutionals to build on this. But this is early stage. This is currently in the discussion. So it's a very good question. So this is coming up.
Yeah, and about liquid staking for Bitcoin, we heard about Babylon and other projects like for liquid staking. What do you think? Is there some maybe news about liquid staking on ICP?
So there will be, I think there will be coming something up. I'm not sure whether I can talk about it now.
I mean, it's on a plan, right?
Yeah, so I heard about things, yeah.
It's forward on the horizon, like.
Yeah, you will see, you will see. So any other questions? Yeah, please.
What's the underlying consensus?
So it's the ICP, it's its own consensus protocol that, so it's essentially a consensus protocol that's permissioned in the way that you have a fixed set of nodes in each subnet, but the way those nodes are governed, so the way that's decided which node comes in is with an open DAO. So it combines the openness of a DAO-based approach and then the higher performance of a permissioned consensus protocol. This gives the subnets a very, very high throughput of more than 1,000 transactions per second per subnet. And even more with upcoming optimizations.
And what about the data storage on ICP?
Yeah, data storage, so it's replicated storage in each subnet. Each subnet has currently 750 gigabyte of replicated state, where you can run your smart contracts in and store your data in, and this will grow to maybe 3 to 5 terabytes in the next 1 to 2 years by protocol optimizations, and then the 5 terabyte is roughly the limit we have with the current hardware. And what we will do in the future is, so there are plans for having another storage scheme which will use erasure coding to have much, much higher storage, much more storage available, like order of magnitude more for lower price, but accessible at a higher cost, as you can see.
One more question.
Yes, please.
We are using it in different countries, in Indonesia, for example.
Yeah.
In Asia and in Europe, and we have different speed. What is the solution for like what's news about the speed right now?
So you're talking about network speed.
Yes.
Yeah, so so when you run internet computer nodes, you have minimum requirements on the bandwidth. So you need to ensure that you are in data center and buy quotas for certain bandwidth per node. So I think if you run, I don't know exactly what it is, but I think 300 megabits per node you should have. This is way enough. So big node providers have a 10 gigabit line, usually small node providers have a 1 gigabit line. So if you think 4 nodes you can handle with 1 gigabit, that's working well, which is usually okay in most regions from a pricing perspective, except for in very remote regions in Africa it can get expensive. Also Asia partially.
Okay, from otherwise, there is a news about the new law, HR 4763, I think, as far as I know, in the States. And what about the regulations?
Maybe you can take that one offline.
Let's take this offline. I'm also not a lawyer, so maybe I'm not commenting on legal questions.
Fantastic. Jutta, thank you so much for
We
taking
can
time.
chat offline if you want, yeah.
Yes, of course.
Wonderful. Thank you. Let's
Okay,
give him
thank you
a last
very
round of
much.
applause. Thank you.